Well, greetings, budding physics fanatics. Now, I have no idea why I just said that, but we just got done studying two-dimensional motion. Doesn't mean we're really done with it, though. We are transitioning into uniform circular motion, horizontal circular motion, vertical circular motion, and actually simple harmonic motion. So this is not limited to one dimension, but it's more into the dynamics of 2D motion, even though we're not going to deal with twisting force or torque per se. But let's get going, and you will see some connections from the past. Some general ideas. When an object moves in the circle, the direction of the centripetal force is, yes, this is review, always toward the center. The centripetal force is always the net force. The centripetal force itself, this is not a force, really. We call it centripetal force, but it's the net force, which is the sum, vector sum, of all the real forces acting on the object in circular motion. They're either contact or non-contact, but the only non-contact force studied so far is, that's correct, gravitational. We haven't studied it that much, but we have encountered it, and it's a non-contact force. Now, the equations we've encountered. Newton, F equals ma, which means sum of F is ma. Correlated with that is weight, which has got the same form. It's mg, g being the acceleration. For circular, vertical, not vertical, but circular velocity or circular speed, distance over time, 2 pi r over t. Centripetal acceleration, 2 pi v over t, which is v squared over r, which is 4 pi squared r over t squared. Look familiar? I hope so. And f of c, we just add the m in front of all those. So we get m2 pi v over t, mv squared over r, m4 pi squared r over t squared. And there's the complement of basic equations that we've already learned, and we will move forward with some additional ideas about circular motion. We are now going to embark on a little primer on horizontal circular motion, using several examples showing how the forces add up to the centripetal force. So basically, some examples where you're actually moving in a horizontal circle, like we see here on this whirligig that you might still find at Great America. Assuming that that park exists when you're watching this video. It does in 2013 still. Two real forces acting on the rider. Well, we're going to look at that. You can visualize what those are, hopefully, resulting in FC acting inward, because that, in fact, is what the person is really doing. They're in a horizontal circle. So we have the weight acting straight down. And so we're thinking free body force diagram here, okay? Then we also have tension in the cable. So tension in the chain or rope cable, whatever it is, there it is. So I'm kind of thinking right now of the person swing combo is the object, and those are the two real forces. There and there. That's it. And so how do they provide for us the centripetal force? Very easy. Add the two forces. Forces are vectors, so there's the tension. Let's add the weight to it. You already know how to do this. Tail to tip addition of vectors. And watch how it gives us the centripetal force. Voila, there it is. So, we see that Fc, or the centripetal force, is the vector sum of all the real forces acting. And that's how it goes. Fc itself is never identified as an actual force. It's the result of these two real ones. So now we're all warmed up. We'll do some more examples momentarily. Let's just summarize some of that. Sum of the forces is Fc. And we now see how it worked. And it's always ma, but in this particular case now it's ma sub c. In other words, it's m times the acceleration, which is a centripetal acceleration. As a vector equation, we would say then that sum of the forces vector t plus vector mg equals FC. There it is. What role does friction play? This is just review. It's the result of the adhesive and cohesive forces between molecules and atoms. It arises when there's a normal force, two surfaces pressing together. Right? That's a contact force between two surfaces. And when one surface slides over the other, there's a retarding contact force. That's parallel to the surface and usually opposite the direction of motion. And it's called friction, symbol F. So this is something that you already know. And now let's move on to some additional examples. In the next example, let's consider a car on an unbanked curve. So here it is looking from above. The car is going around the corner. And if it wasn't for friction, I mean, if this was glare ice, it would just sail right off the road, right? So friction is needed to hold the car in place on the road. So how does that work? Well, we have, if the car is moving in a circle or in a curve, FC pointing inward. We know that has to be the case. So the net force is FC acting inward. So how does this come together? Well, let's look at a front view. So if this box here is really a race car, and we're looking at it, we're standing here looking toward it like this. So here it is. Let's take a look at these forces. We got gravity. We know it acts straight down. Let's put it in. Then we have normal. Normal acts straight up. And in this situation, hopefully you'll remember, no inclined plane or anything. The normal equals the weight. Then in addition, we have friction. Which way must friction act? It's not acting behind it. In this case, it's acting to the right. The road is actually shoving on the car, pushing it inward via friction to enable the car to make the trajectory around the corner. So sum of the forces as vectors, normal plus mg, and those two are 0, they just cancel, plus friction. So sum of F is friction, and that's centripetal force. The real force providing the centripetal force is friction. All right, we're going to add them together now. There's normal. Let's add friction onto that, tail to tip weight, and you see those three real forces add together to give us the centripetal force. Once again, it makes sense. Now let's look at a car on a bank curve at what I'm going to call the ideal speed. So here's a race car again. Now you can probably visualize or have an intuition about this car zipping around this bank curve. Right now, think of this as a circular track. I can't really show this very well. This is a cross section of it. While it's coming toward you, then it's going to go around in a circle. And, you know, if this car was going 1,000 miles an hour, what would happen? Well, probably your reflex reaction would be correct, which would be that the car would sail right off the top of the road as it's trying to execute the corner. Now, if it's not moving at all, if it's just sitting there, and if this is kind of slick, it'll go, plunk down to the inside here. It'll slide down to the bottom. But if it's going too fast, it'll slide right off the top and off the road. So somewhere in between those two kind of extremes is a situation where it should like float around the corner, and indeed it does. That's the condition where no friction is needed. It's the ideal speed. And you won't feel yourself you won't feel like you're being forced to one side. You will just feel, well, maybe I should ask you to think about how you would feel before I say. I won't say yet. What feeling would you have going around this corner fast, but it's at just right speed? So think about that. The two real forces are gravity, okay, and also normal, because we don't need friction. There it is. Now, I drew normal in such a way that it might give you pause when you consider how I drew that compared to FG. Remember on an inclined plane, the normal, wasn't it smaller? Wasn't it shorter than gravity? Now it's longer. Well, this really lends to the answer to the question about how you feel. Namely, the normal force has to be really big. So I can explain that more. I won't try and do it completely now. But one thing that it has to do is overcome the weight, because there's no vertical acceleration. So the vertical part of the normal equals the weight. So that's a key concept. You might want to listen to that sentence again. And just in brief, this needs to be so big because the road literally has to shove on this car very hard in order to provide the sufficient centripetal force to go around the corner. And the part of this normal that basically is just the normal that does that. FG doesn't do that. It has no inward component. So the inward component of the normal has to equal the centripetal force. So those two requirements together make the normal large. So there's FC. Now, let's see how that plots. There's normal and weight. And when you add those together, you get FC. Indeed, the real forces add up to the centripetal force again. Normal plus mg equals FC. The car is banked. FC still points inward. So I hope you believe that. We'll do a couple more examples just to drive the point home a little bit more. Okay, I know this video is going to get a little long now, but you can handle it. We'll be done soon. After these last two examples, a motorcycle in a lean. It's kind of fun looking, isn't it? All right, so it's at a lean angle from the vertical of theta, FC pointing inward, going around a corner and doing this. How does that all work? Three real forces acting on the motorcycle. Gravity, all right, normal, and what else? You guessed it, friction. Let's put them on here. There is gravity. I'm applying it right kind of toward the center of mass of the motorcycle. I'm going to draw the normal upward. Here's the surface of the road. Remember I said perpendicular to it. Now, we could alter that definition slightly for this situation, but let me leave it at that for now and show that, friction pushes this way, the road's friction shoving on the tire, okay, to the right. Let's see how this would add up. Sum of F, normal plus mg plus friction should be FC. All right. Now, why doesn't the bike tip over? Well, if you think about where this road force, the normal and the friction is applied, you have this normal that's basically overcoming the weight, pushing inward at this point. It's really hard to demonstrate just with this little virtual laser pointer, but if you push real hard inward like this to accelerate this mass to the right, if you do it there, it's going to produce a twisting force that's going to have the effect of rotating it back up the other way. Well, put it this way. If this motorcycle was vertical and you push real hard on the bottom of the tires, it would rotate it over to the left and it would fall down. His head would crack onto the pavement somewhere out here, but it would still rotate around like this. So it's all in balance, accelerating this way while tilting into the turn. If you put a meter stick in your hand at this angle and accelerate this way, the meter stick can maintain its angle with the vertical while being accelerated in. All right, that was a lot of words. I can perhaps demonstrate that for you taking my class. Well, it's at the point of contact that force is applied, and that makes it all work. Let me show you how these forces add up to FC. There's FC, we know it has to be. Here's that angle. Let's go ahead and draw the normal, and then tail to tip, we'll draw the friction, and tail to tip, we'll draw the weight. And they add up to the centripetal force. Yay! The crowd cheers. Now, before I do a plane in a turn, the last one, I mentioned that the normal is, could be thought of in a different way. If you look at this normal force and the friction force together, guess what? They make a road force that's pointed along the dotted line. So back in the original drawing, that road force collectively of the normal and friction is, on a trajectory. It's positioned right along the direction of the motorcycle, symmetrically right through it. Now you could consider that just normal, because really there's a distortion in the tire down here, and so the road is kind of like shoving directly onto that. But this is another way to think about it. We're not going to combine these two into what we call a road force, but they are both produced by the road. So we'll leave them as normal and friction. Now, a plane. Here comes a plane flying sideways, which could happen in a typhoon or some insane other situation. I've had that happen to me before, actually. So that's another story. FC, all right? If it's in a lean, it's in a horizontal trajectory in a circle, a horizontal circle. So coming at you and then swinging around, but staying at the same elevation, pointing inward. Forces are gravity and normal. Now, normal in this case is going to be, if it's not the table down here, it's the surface. What's the surface? It's an air surface. So let's consider that. So there's weight, and then we have normal. Doesn't this look a lot like the race car on a just right bank curve? Well, that's exactly what it's like, because this is a just right bank angle for the plane. So here's the vector equation that makes it all work. Here's FC. And we have the normal, and we have gravity, and you see how they add up to the centripetal force. Now, I'm just going to draw this in slightly more detail. So here's that. Now I put the angle down here. Well, really it's there, okay, with respect to the vertical, but these are both the same angles. Now, if you're confused on that, maybe the best way to visualize it is see this normal along which the plane's wings are oriented. This dotted line is perpendicular to this all the time. The normal is perpendicular to the surface. So think about tying this line and this line together. Then if you rotate the whole thing down and reduce theta, this angle reduces at the same rate. If you didn't understand that, think about it in your own way. But those angles are both the same. Here we have weight. Here we have the normal. And there is the part of the normal that gives you the inward force, FC, which is normal times the sine of the angle. If you take hypotenuse, sine of this, you get the component out here, like opposite side, but that's what this is here, right there. Normal sine of theta. So FC is n sine of theta. That will be useful. We're going to progress through this further a little bit later and provide additional detail as necessary. But this is a good start. That the centripetal force is related to the normal through the sine of the angle. We'll see you next time.